Hello everyone, this is my lecture number 17 on network theory, and today's topic is complex frequency and immittance functions and concept of pole and zeros. Myself Dr. Arvindo Sundar Das. I am working as assistant professor in Department of Electronics and Communication Engineering in Swami Vivekananda Institute of Science and Technology, Kolkata. Now, first, let me tell you the concept of complex frequency. The operational method studied by the Laplace transformation will be used to introduce the concept of impedance and admittance function or immittance function. Now, immittance function is basically impedance and admittance is what? Nothing but reciprocal of impedance. If impedance equal to Z, admittance Y equal to 1 by Z. So, impedance is admittance is reciprocal of impedance or impedance is reciprocal of admittance. Now, impedance and admittance, these two words, now we can take im and we can delete this p-dance term im, and from the admittance we can take mittance. So immittance. So immittance function. That is the combination of what impedance and admittance. As a whole, it is called immittance function. Now, already you have seen that the solution of differential equation for RL, RC and RLC circuit has given rise to time domain function of the form k e to the power st, where k is a constant that can be derived by analyzing the initial conditions of the circuit, and e to the power st, in that case that means it is exponential term, exponentially either decay or increasing. Now here s is the complex frequency, or is a complex number, which is s equal to alpha, sorry, sigma plus j omega, sigma plus j omega, where sigma is the imaginary part of s, which is represented or interpreted as radian frequency. Okay, and it appears in time domain in the form of sin omega t and cosine omega t, and here this sigma is Nepper frequency. Now this omega has the radians per second and may be expressed in frequency. In frequency, omega is nothing but 2 pi f, or you can write as 2 pi by t if t is the period. Now this s equal to sigma plus j omega is defined as complex frequency, and this sigma is known as Nepper frequency, that is the real frequency of the complex, and the imaginary part of complex frequency is the radian frequency, and real part of the complex is Nepper frequency. Now the physical interpretation of complex frequency appearing in the function e to the power st can be studied by considering a number of cases for the values of s. Now what we can write, e to the power, instead of s we can write sigma plus j omega whole t into t, right? That means what we can assume, that omega equal to 0, then the sigma value can be a positive 0 or negative value. Okay, so now first case, if we assume omega 0, then in this term what we can write, e to the power sigma t, right? If sigma is say 0, then what, if sigma is 0, then e to the power 0 is 1. So it is a steady state curve or a 1 or a DC response. Okay, that time omega is 0 also. Okay, now say sigma is positive value, that means e to the power sigma t, that can be e to the power 2t, 3t, whatever the value it may be, 0.5t. That means e to the power positive value, that gives you a exponential curve which is exponentially increasing. So that gives us exponential increase curve. Now when sigma is negative, e to the power minus 1t, minus 2t, minus 0.5t, then when sigma is less than 0, it will be a decreasing, exponentially decreasing curve. Okay. So when sigma is 0, a constant curve, sigma greater than 0 exponentially increasing, sigma less than 0 exponentially decreasing, sigma greater than 0 exponentially increasing curve. So this is the part of the complex frequency. Now when sigma is 0 and we have a j omega term only, then what will happen? We can write k to the power plus minus j omega t, and according to the Euler identity we can write k cosine omega t plus minus j omega t. Now in this term what we can observe is cos omega t is the real part and j sin omega t is the imaginary part. So real part, this point, its value is say 1. So here it is 1 and this curve is nothing but the cosine curve which starts from 1. Okay, cosine 0 is 1, angle is 0 here. Now when angle is 0, imaginary part value is also 0. So it is started from here. So 0 to it will go on. So this is your sine term. So this is your cosine term and this is your sine term according to the phasor diagram of this particular signal. Now say if we have both sigma and j omega term, say when sigma is positive, it can be positive, it can be sigma can be negative. When sigma is positive, it will be sigma t into it will be what j omega t. Okay. Then what we can write, that real part of that is k to the power sigma t cosine omega t, and imaginary part is k to the power sigma t sine omega t. Right? If we if you decompose this into Euler identity, now it will be for sigma t, that means it will increase. So in that case the graph will be what, that is, it is exponential, it is a oscillatory graph and the amplitude is con, increasing continuously. Here amplitude is this, then increases, so it will go on increasing its amplitude. It start from 1 because it is cosine, it start from 0 and amplitude is increasing. So this is for e to the power sigma t cosine omega t or e to the power sigma t sine omega t. Amplitude is increasing. Now similar thing, if we take e to the power minus sigma t cosine term and k to the power minus sigma t sine term, then what we can see here, that for cosine term it is started from 1 and amplitude is, it is oscillatory but amplitude is decreasing by amount of alpha value minus alpha, it is decreasing, amplitude is decreasing. Similarly for sine also, amplitude is decreasing. Okay, so this is the concept of the complex frequency that we have used in case of Laplace transform also, that is alpha, sigma and omega, what will, by putting some values, how the response will be. In case of Laplace transform we use that Laplace transform of ft which is equal to fs, that is equal to integration of 0 to infinity ft e to the power minus st dt. The s is nothing but this sigma plus j omega. Okay, and when sigma is 0, less than 0, greater than 0, what is the response that we have seen for cosine and sine term when omega is there. Okay, if sigma is positive greater than 0, then amplitude is continuously increasing, oscillatory function, and amplitude is decreasing, so it will reach some steady state value but it will go to some infinity value or amplitude when amplitude is increasing. Now say, let me just tell you about terminals and terminals pair. Now consider an arbitrary network made up entirely by passive elements. To indicate the general nature of the network, let it be represented by a symbol or a box. So this is a box. Now we can take two wire, okay, two wire, so that we can connect a voltage source or current source here, that is the driving source, we can connect here and we can find out some response. Okay, response here that is inside the box. Now so this is called a two terminal, or say one terminal pair, one terminal pair, that means it has only two terminals. Okay, so one terminal pair. Now you can have it, or you can say this is just one port network. One port means we have two terminals. Okay, because we always require two terminals, because current there must be a closed path to make the circuit to be completed. Okay, so now in this case we can have, this is a two terminal pair or say two port network. one port and two port. One can you can assign as input port where we can apply some excitation. Here we can observe the response. That is a two port network. Now this is a n terminal pair network or n port network. Okay, we can have driving point. We can have voltage source in say two ports and other are response port, or one port is the uh, driving point port where we are connecting the excitation, others are the response. So like that way we can find. Now driving point immittance. What is that? That the transfer for impedance the transformed impedance has been defined as the ratio of voltage transform to the current transform. That means this is already known. That is nothing but R resistance equal to V by I. So this impedance is nothing but Vs by Is. It is written in terms of Laplace. Similarly, transform admittance can be written as Ys equal to Is by Vs. So that is nothing but Zs equal to 1 by Ys. Now the voltage transform and current transform that define transform impedance and transform admittance must relate to the same pair of terminals. Okay, that means say if you connect here a voltage source, okay, and if you see here current here, then looking at this point, V by I is the impedance and Y is the I by Z. Okay, so same pair of terminals. Now the impedance or admittance found at given terminal pair is called driving point impedance or admittance or driving point immittance. The two quantities are assigned one name immittance, a combination of impedance and admittance that already I have told you. Now, the driving point immittance of a network is found by combining the impedance term of inductor, capacitor, and resistor. For resistor, it is only R. For inductor, in Laplace domain, it is SL. For capacitor, Laplace domain 1 by CS. Or admittance parameters R, it will be G. SL will be 1 by SL. For capacitor, 1 by CS becomes CS by adding, multiplying, or dividing. Now, this algebraic combination of terms results in an immittance function in the form of a quotient of polynomials such as a0 sn plus a1 sn minus 1 up to an, b0 sn plus b1 sn minus 1 up to bm. Okay. Now, this is the rational function of s, okay, where n and m are the integers. In the above equation, m is the order of numerator, m is the order of denominator polynomial. So this is a rational number which is nothing but ratio of two polynomials, numerator polynomial and denominator polynomial. And polynomials are nothing but the integral positive power of a variable. In this case, this is s, variable s. And this a0, a1, b0, b1 are the coefficients. Okay. Now say take us one example. Driving point immittance, say a RLC series circuit. Now say we have to find out ZS. ZS is nothing but R plus SL plus 1 by CS. Okay. Now we can multiply that. So what we will get, LCS square RCS plus 1 by CS. Now we can take from here, from numerator we can take. Now in this case, for immittance function, always try to make this a square highest power coefficient. A square is the highest power in this case, so highest power coefficient to 1. So we have to divide this numerator by L by C, and we can divide this denominator by C. Then what we will get, L by C, we can take common of LC here, and from here C, so CC cancel out, so L is a constant term. We will left with S square plus, here we have to divide by L by C, so R by L into S, and here 1 by LC, and here S. So we have this numerator polynomial that you can see here. This is nothing but second order, and denominator polynomial is of first order. Okay. Now see here, this is nothing but ZS is written as k into s with just two polynomials. Okay. Now order can be different. Okay. So this is can be written in rational as a rational function, okay, of two polynomials. Now say another example. Here R and L in series, which is in parallel with C capacitor. So Zs will be what? 1 by 1 divided by R plus SL is the one, this impedance that is in parallel with that, to 1 by R plus SL plus 1 by CS, 1 by 1 by CS, which is CS. So we got this expression after solving. Now we can see here that the numerator polynomial is order first, but denominator polynomial is order second. Now for the previous case it was opposite, okay, and here the constant is L, but here constant is 1 by C. So according to circuit, our impedance function may change, and it will change the order of the polynomials also. Now say, what is transfer functions? So this is how you have to find out the admittance or impedance function or driving point function. Now what is transfer function? But the concept of transfer function is identified with networks having at least two terminal pairs or two port network. Okay, so we have two terminal pairs or two port network, one port, second port. We are also interested in the ratio of excitation and the response for the two terminal pairs. In case of one per terminal pair, we are finding out only the driving point immittance, either impedance function or admittance function. Now for transfer function, we will require excitation and response. Now the function relating the transform of a quantity at one terminal pair to the transform of another quantity at another terminal pair is given the name transfer function. Now in computing the transfer function, all the initial conditions are assumed to be 0. This is the main point that you have to remember. Now in that case, there are several forms of transfer function in electrical networks. One is the ratio of one voltage to another voltage, that is called voltage transfer ratio. One current to another current, that is called current transfer ratio. And one current to another voltage, or one voltage to another current. Okay, that means we have to apply a voltage here, and we can measure a voltage here, then voltage by voltage. Okay, we have a current, measure current here, then current by voltage or voltage by current, or say you apply a current source here, measure a current, then current by current, or measure the voltage by current. So this is how we can make the transfer function. So transfer function can be either V out by V in or V2 by V1s. Okay, and we can find out the, if we find out V1 by I2s, that is the input voltage and output current, that will be called transfer admittance Z of 1 2. 1 is the first one, port 1, 2 is the for port 2. So this is transfer impedance V1 by I2. Now similarly we can find out the I2s by V1s, that will be called transfer admittance 2 and 1. And for this case V2 by V1, that will be known as the voltage gain. Okay. So why this is called transfer? Because one is port 2, another one is for port 1. Now the transfer function is determined by the network immittance and can also be reduced to a quotient of polynomials. So GS can be written as PS by QS form, which is the rational function of two polynomials. Okay. The transfer function has the same general form as the driving point impedance function. Why? Because say in this case, okay, let us take example of transfer function. Now say this is the circuit R and C. This is, you are applying a voltage source V1, and across this you have to measure the voltage V2. So what is the current flowing through this is say I1s. Okay. Now V1s equal to what? Nothing but I1s into R, I1s into 1 by SC, which is equal to V1, and V2 nothing but I1 into, or I into 1 by CS, that is across capacitor. Okay, now we can find out V2 by V1, which is the transfer function. So if we put two equations here, we will get this particular function. Okay. Now what we can see here, that this is nothing but V2. V2 output is total voltage. This is nothing but the voltage divider circuit, right? So we have found out this transfer function. Okay. Now transfer function has numerator polynomial of zero order and denominator polynomial as first order, because here x to the power 1, here don't have any s term, so zero order. Yeah. Second example, another example, in that case instead of r we have a inductor. So V2 by Vs, what we can write? Voltage divider rule. So 1 by Cs divided by 1 by Cs plus SL into V1. So V1 we can take it this side. So this is nothing but we are getting this transfer function. So we can solve it and we get that numerator polynomial 0 order but denominator polynomial of second order. Previous case it was first order, now it is second order. Okay. Another example, in that case say what we have, these two resistance capacitor in parallel, so we can find out Z equivalent of that. Okay, that is say 1 divided by 1 by Cs plus 1 by R1, so you got this value. Okay. That is R1 into 1 by Cs divided by R1 plus 1 by Cs, so we'll get this value, and Gs will be equal to what? V2 by V1s, which is nothing but V2 is what? Nothing but R2 divided by R2 plus Z equivalent, okay, into V1. I can take it that side, so that will be equal to Z. Okay, now you can put Z equivalent value here, and if you solve algebraically, you will get this particular expression. Now in that case you can see that polynomial of numerator polynomial is of zero order, second order in denominator polynomial is also of zero order. Okay. Now say let us find out one another point, that is pole, what is poles and what is zeros. Now say for this simple circuit, resistance, inductance, capacitor, what is the ZS that we can find out? With these two in parallel, so SL into 1 by SC divided by SL plus 1 by SC, that is similarly R1 into R2 divided by R1 plus R2 plus R. So we got as ZS. Now we can solve it, and we will found this particular expression. Okay, here we have a constant term, so K. Here this is the term we can write as in PS, and this term we can write as QS. So this is the rational function. Rational function is the rational function is nothing but so this one is nothing but the rational function. Okay, is the ratio of two polynomial. Polynomial is finite series with integral positive of the variable. Okay, so that is K PS by QS we can write. Now this term PS is a polynomial. Now polynomial can be written in terms of its roots as factor. Now this is x square plus 4s plus 1. So we can factorize that in some manner, x minus z1 into s minus z2. Similarly for the denominator, s minus p1, s minus p2. Now from this particular case, numerator, what is the root? That is nothing but minus 1 by 2rc plus minus root over 1 by 2rc square by minus 1 by lc. And for p, for the denominator, the roots are nothing but plus minus 1 by root over lc. Okay, that are the roots of the quadratic equation that we got. Now after factorizing that, now from this what we can say, that suppose now if we put one of the root value z1 in this equation, then what happened? Numerator terms become 0, z1 minus z1 it becomes 0, or it is z2, z2 minus z2 is 0, that means zs function becomes 0. That means the roots of the numerator polynomial makes zs function, this function, equal to 0. That's why this the roots of the numerator is called as zeros, and if we put the roots of the denominator here, that is p1 or p2, what happens? This will be 0 here, numerator denominator, then total function will be something by 0, it becomes infinite. That means for the roots of the denominator, what happens? The function becomes infinite or it blows up. That is why it is called pole. So 0 is the roots of the numerator polynomial, poles are the roots of the denominator polynomial. Okay. Now similar thing, that two polynomial constant factorized. Okay. Then so that network for the variable, when the variable s has the values of s1 s2 sn, the network function vanishes or 0. Such complex frequencies are called zeros of the network function. And when s has the value of this sa sb up to sm, that is for denominator, the network function becomes infinite. Okay, that it becomes 0, so network function becomes something by 0, infinite, or it blows up. That these complex frequencies are called poles of the network function. Okay. So zeros make the function equal to 0, and poles makes network function infinite. Now poles and zeros are important in network theory or in control theory, in signal systems, everywhere. A comparison of at the last two equations shows that a network function is completely specified by its poles and zeros and the scale factor. So here you can see that network function can be derived, can be explained by the zeros, poles, and this k is the scale factor. Now in that case, both both 0 and infinite value of s are possible pole or 0 location. Now when n greater than m, now you can see here, n is the order of the zeros, m order of the poles. If n greater than m, that means number of zeros are higher. So what happens here? When n greater than n, s equal to infinity is a pole of order n minus 1. N is 0 for 0, number of zeros is higher than m. So actually what happens is that number of poles and zero must be the same for a particular transfer function. So if we have say 6 poles, zeros, 4 poles, then 6 minus 4, that is 2. 2 poles will be at s equal to infinity. If n less than m, that means pole is higher number, then s equal to infinity is 0 for order of m minus m. If n minus m, n equal to m, then s equal to infinity is neither a 0 nor a pole but an ordinary point. Now total number of zeros is equal to total number of poles of a system. That you have to remember. Now let us take for example, a network function is given like this. So here what we have, 1, 2, 3 zeros, 1, 2, and here 3, 5 poles. Now s plus 1. So what we can write, s plus 1 equal to 0. So s equal to minus 1. So zeros will be at minus 1. Other two are at minus 2 plus j1, another minus j1. So how we have to find out? Take this one equal to 0, s equal to what? You can find out. Now for poles we have s cube, that means s equal to 0. So we have sa sb sc 0, then s equal to minus 3, s equal to minus 5. So in this is a pole 0 diagram or s plane. We have, this is your last, this is your sigma, x axis is the sigma, and omega axis is the vertical one. So this is your real, this is your imaginary part. Now 0, a small circle is used to designate the location of a 0, and cross is the symbol for the location of pole. Now zeros are at minus 1. So at you can see here, minus 1 there is a 0, and two zeros are also there which are at minus 2 plus minus j1. and we have poles at -3 cross sign, -5 cross sign, and we have 3 poles here at origin s equal to 0. Okay, but we have 3 poles. Where is the other 2 zeros? We have 3 zeros. Where are the other 2 zeros? The other 2 zeros must be at infinity. So 2 zeros at infinity. Okay, because pole number of poles is higher than zeros, whereas the other zeros that goes to infinity. Okay. Now poles and zeros designate the critical frequencies. At poles, the network function becomes infinite, while at zeros, the network function becomes zero. At other complex frequency, the network function has a finite non-zero value. In terms of driving point immittance, poles and zeros have easily visualized meaning. Suppose we have is Vs equal to Zs Is. Now, 0 of Zs. Zs is the impedance function. Now, zeros of that makes this function equal to Zs equal to 0. If Zs equal to 0, then Vs equal to 0, irrespective of the value of current Is. That means it is a short circuit, right? Voltage becomes 0 if Zs for a 0 of Zs, 0 0 of Zs function makes Zs equal to 0. That means Vs becomes 0 irrespective of the Is. That means it is a short circuit. Okay. Now similarly, what we can say that Is equal to Ys into Vs. This is for admittance function. Z equal to 1 by Y. So I equal to Y into B. Now Zs and Ys is reciprocal of each other. Now the zeros of Ys nothing but poles of Zs. Okay. So zeros of Ys is nothing but poles of Zs. Now in that case, the zeros of Ys, what it will do? Zeros of Ys makes Ys equal to 0. If Ys equal to 0, then Is equal to 0 irrespective of the voltage. Right? Now Is equal to 0, that means what? An open circuit. Okay. So from that what we can conclude that zeros basically provides us a short circuit of the function, pole provides us open circuit of the function. Okay, so zeros will give us the current response because it is short circuit, and poles will give us the as it is open circuit, it gives us the voltage response. Okay, now say example for a capacitor, the driving point impedance is Zs equal to 1 by Cs. Okay, now in this case, that network, in this network pole, it has a pole at s equal to 0, 1 by Cs, pole at s equal to 0. That means what? At s equal to 0, what will happen to Zs? That becomes infinite. Okay, okay, so at s equal to 0, which is nothing but omega equal to 0, it becomes infinite. Okay, and it has a 0 at location infinity, right? So at omega equal to infinity, it becomes a short circuit. Okay, that means capacitor, what is the function of capacitor? That is xc equal to 1 by 2 pi fl, that we know fc. That means for f equal to 0, it is infinity. How we can say? From this function we can find out that z is equal to 1 by cs. So pole is at s equal to 0. Okay, that means at s equal to 0 means omega equal to 0. Omega equal to 0, circuits blows blows up, that means it goes to infinity. Okay, and in at 0 is at s equal to infinity because there is no s value, so it is at s equal to infinity. That means at infinity it becomes short circuit. Likewise for an inductor, driving point impedance is s equal to sl, z is equal to sl. Now here what we can say, 0 is at s equal to 0. That means at omega equal to 0, this function becomes 0, or that is short circuited. Okay, at AC equal there is a no, that pole is what, there is a no denominator term, but pole should be at infinity. Okay, that means at omega equal to infinity it becomes open circuited. So that is the actual meaning of inductor and capacitor that you know previously, that we can extend with respect to this pole zero concept. Okay, Now, say, say Z is equal to this one already I have mentioned that zeros of zeros of Zs, Ds equal to Zs, zeros of Zs make this Zs function equal to 0. So Vs equal to 0 irrespective of I. That means it is a short circuit. Okay. Vs equal to 0 is short circuit. So we can have the current response because there is some current is flowing. Thus zeros are associated with natural current response, and if we take the admittance function is equal to ys into vs. Now in that case, zeros of ys is nothing but poles of zs because those are reciprocal of each other. Then zeros of ys, it makes ys equal to 0. Then I equal to 0 irrespective of the voltage. Now I equal to 0 means an open circuit for a finite voltage. So thus poles are associated with natural voltage response. Thus we can write Z is equal to K PS by QS, and this PS we can write as summation of this is a continued product. This is a continued product of I equal to 1 to M S of minus S minus ZI, that is factorized. Then continued product I of I equal to 1 to N S of minus PI factorization. Then IT current response we can get from these zeros, that is summation of I of 1 to M AI e to the power ZIT, that is in that particular form K e to the power ST form, and where the S is the Z value, and this denominator part gives us the voltage response 1 to N BI e to the power BIT. Now say some port 0 and poles locations. So this is a function where we have s equal to minus 1 minus 2. So minus 1 minus 2 is the 0 location, pole at minus 4 minus 5 minus 8. Okay, and another 0 should be there at infinity because we have 3 poles and 2 zeros. So another 0 should be there at infinity. Now say exponential term e to the power minus alpha t ut. If you convert into Laplace domain, 1 by s minus alpha. So it is at s minus alpha here. Now if it is exponentially decaying, if it is e to the power alpha t ut exponentially increasing, that should be at right hand side plus alpha. Now sine term, sine beta t is nothing but beta by a square plus beta square. So in that case, it is on the imaginary axis plus j beta minus j beta. Now damped cosine function, it will be minus alpha t cosine of beta t, that is s minus alpha at s minus alpha, that is 0, and poles at minus alpha plus minus j beta. So two complex poles are there. Okay. So poles and zeros can be real and complex function. Now this is one chart. What it is showing that when there is a pole at real axis, what happened? That will be a exponentially decaying nature. That shows exponentially decaying nature. Okay, and if the pole is closer to the imaginary axis, then it decays slowly, and if poles goes away from the imaginary axis, it decays faster. Now, if we have a complex poles at left hand plane, left side, left half plane of the S plane, complex pole, what it shows, it is a damped cosine or sine function or damped function, damped oscillation function. It is going down to 0. Now, if it is close to j omega axis, imaginary axis, what happened is it will take more time to settle down. If it is away from the j omega imaginary axis, it will reach steady state faster. Okay. Now pole 0 and stability. Now pole and zeros of the system are plotted in S plane to check the stability of the system also. If all the poles of the system lie in the left half plane, the system is said to be stable. Okay, that means at left half plane, all the poles at left half plane, then it is stable system. If any pole lie in the right half plane, then system said to be unstable. If poles lie on the imaginary axis, the system said to be marginally stable. Sometimes it can be unstable also. Anyway, so now what happening here? You can see here, that is a complex pole is here. What it is showing? Damped oscillation, right? It goes to zero. That means it is stable. It goes to a stable value. Either it can be zero or some constant value, something like that. Now, if pole in right half plane, what happened? It is going increasing infinitely, and it will go to infinite. Now, if it is going to infinite, then the system is not stable. A system basically blows up. Okay. Now, if it is on real axis, that means exponentially decaying. If it is in left half plane, for right half plane, on imaginary axis, what happens? It goes increasing exponentially. It goes to infinity. So that again it blows up. That means what? For right half plane, we have unstable region. For left half plane, it is stable region. Now we have already shown this. Now say on the j omega axis, if there is a pole, what happens? A pair of purely imaginary poles on the imaginary axis of the S-plane implies that there will be no decay. If it is on imaginary axis, there is no decay. That means the system acts as a pure oscillator. That means, see here, for these two pole, complex pole, and complex pole always comes in conjugate pair. Okay, so it will continue to oscillate forever. Okay, and value of frequency increases. So this frequency increases. How you can see that time period is decreases. That means frequency increases. Okay, so this is the concept of poles and zeros, and these poles and zeros are very essential parameter that is used in circuit theory, in control system, in signal system, in digital signal processing, to analyze the system. So always is there, that is the concept, that if poles are on left hand side or left half plane of the S plane, then the system is stable. If it is on right hand side or right half plane, then it is unstable. If it is on imaginary axis, it is marginally stable. Sometimes it is unstable too. Okay, so thank you. This is it for today. So in this lecture, what is the main point that we have to understand? That is what is poles and zeros. Okay, and what is the physical interpretation of poles and zero. In with respect to circuit theory, the main physical interpretation is that zeros makes the function, network function, zero. That means short circuited. That means we can get the current response. And poles makes the network function infinite. That means it makes the transfer function open circuited. That means we can find the voltage response of the circuit. So zeros helps us to find out the current response. Poles helps us to find out the voltage response. Okay. And the proof that I have shown you, that is in just like 1 by Cs and Sn. Okay. So, so thank you so much. This is it for today. Thank you.